Hello, in this video I'm going to show you some of the example of moment for 3D settings. Okay, so you already learned the theory behind it. Actually, moment in 3D cases would be much more easier than you think. Okay, if you have a little bit knowledge about vector, actually you learn how to convert like the forces into vector, then basically 3D cases is very easy to do. Now let's start with the problem number 4-32. You can see here this is your y-axis, this is x-axis, and this is your z-axis. There is a steel frame here which is 0.5 meter in that direction, then parallel to the y-axis 0.4, and then going down like 3 meter. And here is point C, and you have a force vector working at point C, which is 600I, 800J, and 500K. So this one is basically asking to find out the moment of that force at point A. Now, first of all we have to just we know that the moment at A for 3D cases is basically position vector from A to C cross product of force vector. Okay, so the position vector AC means like any position vector from point A to any known point on the line of action of the force. Okay, let's say for example, if I have a point here and I have a force here, then if I want to find out a moment at point O, then basically if these are known points here, let's say this is the force vector, then moment at O is basically any position vector from O to A, or you can say moment at O is basically ROB into F, or the moment at O would be ROC cross F. For 3D cases, you don't have to worry about whether this distance is shortest distance or perpendicular distance. Actually, this cross product will take care of that thing. So if you know any points on the line of action, then basically a position vector from the point at which you are taking that moment to any known point on the line of action of the force, you just find out the position vector of that and then cross that one with your force vector. Okay, so let's go back to our problem. You can see the only known point for this line of action of that force is point C, which is basically x direction. You can see 0.5, then y direction 0.4, and 0.3, that's actually 0.7, and z direction is going down 0.3, so that's 0.3 here. So the position vector from A to C so A is basically 0, 0, 0. So you can see position vector from A to C is 0.5I plus 0.7J minus 0.3 k. Okay, that's the position vector. And they gave you the force vector. So your moment at A that would be I, J, K, and then the position vector 0.5, 0.7, minus 0.3, and here force vector, let's say 600 I component, 800 J component, and minus 500 K component. Okay, now you have to find out the determinant of this 3-3 matrix. I know like many of you already know about matrix. If you don't know, just try to go back your vector analysis or this book, like try to see the, like the theory that how you can find out the determinant of a 3-3 matrix. Okay, it's not that difficult. I'll just show you here so that you can understand that one here. Okay, so what we usually do to find out the 3-3 matrix is like by default we usually use like this is positive, negative, and positive sign, and again if you go like this, then it's negative, positive, negative, positive, negative, positive, something like that. Okay, but we don't have to go that far. If I just take like the first, like row, then this one will be fine. Now, what we do, this one is basically equal to I, then you cancel like the row and column for I. So you can just show that 1.7 minus 0.3, 800, and minus 500. This is the submatrix, like only this part here because you cancelled this one. Okay, now for J you can see definitely this is a negative sign here. So you have to write this submatrix for J. To do that, you have to just cancel the row and the column of J. If you cancel this one and this one, then basically you have this, and this here. Okay, so which is 0.5. And then 600 and minus 500. Now basically you have to add this K term here. So for K term you see that you have to cancel this and this. So you have only this here. So 0.5, 0.7, and then 600 and 800. I'm trying to show that one a little bit elaborately, but from the next time actually I will just go and try to do that one in a shortest method. Okay, so what we usually do to find out the value or determinant for a 2-2 matrix is nothing that like we multiply this minus this. Okay, this minus this, this minus this. Okay, so let me write it there. So the moment at A you can see here that's actually minus 500 into 7. minus, and then there is a negative here, 0.3 into 800. That's basically your I, okay? Then minus j, this minus this, so 0.5 multiplied by minus 500 minus 0.3 into 600 plus your k, you can see here 0.5 into 800 minus 0.7 into 600. Okay, now if we just simplify that one, then you can see this is actually 0.7 here. So you can see your MA is equal to, this is minus 350 minus minus plus 240 I, right? And then you can see here minus, this is negative and this is positive, so 250 negative 250 plus 180 j plus 400 minus 420 k. So this is basically minus 110 I plus 70 j minus 20 k. That many Newton meter. So you can see actually your moment here is given in terms of vector. Okay, so if they ask you to find out the magnitude of that moment, that nothing but, here they didn't ask that one though, but if they ask you, you know how to find out the magnitude of this vector here, right, which is root over 110 square plus 70 square plus 20 square. And again, you can just show that moment as a unit vector and find out the angle, this one, the moment is making with x-axis, y-axis, and z-axis. Okay? So let's move forward. Now I am gonna do the problem number 3-40. This one is saying that basically this is an arc which has a radius of 0.5 feet, and you can see from A there is a force working towards B, and the magnitude of that force is 60 pounds. Now it's asking that how much moment this force will create for point C. Okay, now you already know that your moment at C is equal to position vector from C to any known point on the line of action of the force. So it could be, because in that force we can see there is 2 point, actually we know the coordinates at point A or point B. Okay, so we can say like CA cross force vector from A to B. Or we can also say the moment at C is basically R A to B, because B is also a point on the line of action of the force, to AB. Okay? Now you can see here the force is not given in terms of vector, Cartesian vector, so we have to change that force into Cartesian vector. Okay? And then we have to write the position vector for either RCA or RCB, right? To do that, the first thing would be just find out the coordinate for this one. You can see this is 0, 0, 5. This one would be in the x direction 6 feet, y direction 7 feet, and z direction 0 feet, because this is in the xy plane. Okay? Here you can see this is actually YZ plane, and you can see that your x would be 0 because you don't have any values here, and your x would be 5 sine 60 degree, right? So 5 sine 60, and then this one in the z direction would be 5 cosine 60. Now I can definitely simplify that numbers there. Just plug the value of sine 60 and cosine 60. That's actually 0, 4.33, and 2.5. And 2.5. Okay. So now we have to first, find out the force vector, which was working from A to B. So to do that, first I have to find out the position vector from A to B. So B minus A, that's actually 6I, 7 minus 4.33, J, and minus 2.5 K. So that's basically 6I plus 2.67J minus 2.5K. So the unit vector, to find out the unit vector, you need to know the magnitude of RAB. So magnitude of RAB is basically 6 square plus 2.67 square plus 2.5 square. That's basically 7.03. So the force vector, or the unit, let's say the unit vector AB is basically RAB divided by the magnitude of the vector, which is 6 by 7.03I plus 2.67 divided by 7.03J minus 2.5 divided by 7.03K. Okay, so the position vector, the force vector AB, that would be F into UAB. So the magnitude of that force is 60. So you can say this is 60 plus 2.67 by 3.03J minus 2.5 . So your FAB is basically, if you calculate that one, then you get 51.23I plus 22.79J minus 21.35K. Okay, so this is our force vector here. Now we can also write the position vector for either RCA or RAB. Should be RCB. But you can see here that if you see like, actually I'll show both of them and show you that actually the answer is same. Okay. Now let's see that position vector from our CA. So CA is actually 0I plus 4.33J and minus 2.5K. On the other hand, you can see your RCB, that's actually B minus C, so 6I, 7 minus 0, so 7J, and 0 minus 5, that's 5K. Okay, now I'm gonna do that one by one. So if I do that one for, let's say, for this one first, so this one would be I j, k. Then the position vector CA. So C is 0, 4.33, and minus 2.5. Here you see 51.23. This one is actually 22.8. I'll just write 8. And then this one is, actually let me put the, because I'm putting two decimal here, 27, and then this one is minus 21.35. Okay, so if you find out the magnitude, like our determinant of this this one here, let me do it here. So this one would be I. When you are taking I, then you have to cross this one, right? So this minus this. So you can see minus 4.33. Actually, let me put this way. Minus 21.35. And then this one is actually becoming plus, actually should be negative into 2.5. That's positive 2.5 into 22.79 minus j. By default j is always negative, okay? And then you can just see, take this one and this one out. So 0 into this one, that's actually 0. And then minus this one, but there is a negative sign, so plus 2.5 into 51.23 plus k. So this one and this one cancel, so this minus this. So if you multiplied anything with 0, that's actually 0 minus 4.33 into 51.23. That's basically minus 35.4 I minus 128J minus 222. Okay, so that's your answer here. Now you can do the same thing, just changing the position vector from CB. So the only thing this one will be changed here is this line here, okay? Now you can see that 6, 7 and minus 5. So here you can just do that one like this. When you're taking I, then 7 into actually 7 into minus 21.35, okay, minus, and there is a minus, so plus 5 into 22.79, that I, okay, minus j is negative, So if you take this one cancel, so that would be 6 into negative 21.35 minus this one, okay? So minus plus minus, so that becomes plus 5 into 51.23, and then for J or for K, you can see we have to just cancel this one, so 6 into 22.79, okay, minus 7 into 51.23, that, sorry, here is J and there is K. So if you simplify that one, so you will get minus 35I minus 128J minus 222K. Okay? So you can solve that problem with both ways. Okay? Let's move forward. Now I'm going to show you the problem number 4-50. What this one is saying, that there is a manhole which is actually 1 meter diameter or 0.5 meter radius is opened, like from the horizontal 30 degree up, okay? So if there is a force that's working from A to B, then basically you have to find out the moment of that force with point O, okay? But you can see this location of that point A is actually making 30 degree with the y-axis here. So I tried to draw that one, like 2D cases, like if this is your y-axis and this is your z-axis, then basically when you pull that manhole, like cover of the manhole, then basically you can see this one is gonna go like this. And this is your location of the point B, this is the diameter of the manhole cover, okay? So what would be the location for B here? You can see X is 0 because this is YZ plane, and your Y is this, which is 1 cosine 30, and your Z would be from here to here, so that's actually 1 sine 30. So if I plug that value there, that would be 0.866, that cosine 30, and this is 0.5. Okay. Now we have to find out the location for point A. I tried to draw the, like this is your y-axis, this is your x-axis, like your xy plane. So you can see your A, your y would be 0.5 plus, you can see this is actually the diameter here, radius here, which is 0.5 meter. So the distance of A from the x-axis is 0.5 plus 0.5 cosine 30, which is from here to here, okay? And your x is this direction, which is like this one, which is 0.5 sine 30. So the location of A is basically 0.5 sine 30, which is 0.25, and then 0.5 plus 0.5 cosine 30, that actually 0.933, and your z equal to 0. Okay? Now let me put that one here so that it be easier for us to solve the problem. So 0, 0.866, and 0.5 here. For A, the location of A is 0.25, then 0.933, and 0. Okay? So if I want to find out the moment at O, we know the location of O, which is at the center here. So this one is 0, 0, 0. Now once we get these values or the coordinate here, then basically we can find out our force vector as well as our position vector to find out the moment, right? So my moment here is, let's say, moment at O, that should be equal to position vector from O to A or O to B. Let's say I'm just taking O to B cross my force here, force vector. Okay? So if I want to write my position vector ROB, that's actually B minus O, so this is 0I plus 0.866 J plus 0.5 K. Okay? Now I want to, convert my force into Cartesian vector. So I need to know from A to B, the position vector from A to B. So B minus A, so you can see like minus 0.25 I, then this minus this, so that's actually negative 0.067 J and 0.5 K. Okay, now let's find out the magnitude of that position vector. So RAB, that's actually that's actually 0.563. Okay, so the unit vector for AB, that would be position vector for AB divided by the magnitude of the position vector. So this one is minus 0.25 divided by 0.563 I minus 0.067 divided by 0.563 J plus 0.5 divided by 0.563 K. Okay, so your force vector FAB that would be actually your magnitude of your force, which is given here, 450 Newton, multiplied by your unit vector from A to B. So you can see this is 450 multiplied by I minus 0.067 divided by 0.563 J plus 0.5 divided by 0.563 K. Now you multiply that one, then basically you will get your force vector, which is minus 199.82 I minus 53.54 J plus 399.63 K. Okay, now I have to write my moment formula here. So you can see this one has to be is equal to I J K, then your position vector 0.866 and 0.5, and the force vector, which is minus 199.82, then minus 99.9, no, that's minus 53, sorry. $53.54 and 399.63. So if you solve that one now, then basically you get your moment is equal to 373I minus 99.9 J plus 173 K. So that's basically your moment of that force along point O. Okay, now let's move forward. I'll just show you some more problem from here. Basically a little bit different, that like here we are just trying to find out the moment at a particular point. Now I am going to show you a couple of problems where we will try to find out the moment along any axis. Okay, along any axis. Okay, let's move forward. Okay guys, now I am going to show you the problem number 4-52. So which is saying that the lug nut on the wheel of the automobile is to be removed using a wrench and apply the vertical force F, which is 30 Newton, and that's your wrench here. Now saying that determine if the force is adequate to provide 14 Newton meter of torque about the x-axis is initially required to turn the nut. If the 30 Newton force can be applied at A at any other direction, will it be possible to turn the nut? Okay, so to do that, what they are basically saying that you are trying to open that nut here. Okay, now what you are trying to do is applying a force 30 Newton vertical to that, vertical to that direction here. Now this one is asking like whether you can produce enough torque to turn this nut off. Okay, so they are saying that whether you can create 14 Newton meter, you need 14 Newton meter. To move that one loose, okay? So what I have to do here, that since they are asking that how much moment this one is gonna, or torque is gonna create along the x-axis, so my moment along the x-axis would be equal to ux r a to b cross f. That's the formula, right? Ux is the unit vector for the axis at which I'm trying to find out my moment, and RAB, this is a vector from any point A on the axis at which I'm trying to take my moment to any point at the line of action of the force B. Okay, any point at the line of action of the force B. Now you can see here, actually this is point O, this is point A, this is B, and let's say this is C. So you can see here, actually I know the coordinate for B, also the coordinate for C, because this is 0.5, this is 0.3, so this one would be 0.4. Similarly, I know O, the location of O as well as the location of A, both are along the x-axis. So either I can take the position vector from A to B or O to C, that's up to you, that which one you feel more comfortable, okay? Now let's move forward here, that if I want to see, this one is 0.1, so the location for A, let me write it down here, that would be 0.1 m, okay, in the x direction. In the y and z direction is basically 0 and 0, okay? Similarly, if I write that one here, so this one is at the same x here, which is 0.1, the y is negative 0.4, and the z is from here to here, so 0.3 meter. Okay, now you know the unit vector for x-axis is just I. Okay, unit vector for y-axis is just j, and unit vector for z-axis is just k. Not only that, if you have any parallel axis to x-axis, that's also I. Similarly, any axis that parallel to y-axis, the unit vector would be just j. And any axis parallel to the z-axis, the unit vector of that line would be also just k. Okay? So you can see that ux here is equal to just I. I'll just try to say like this is like A to B, the position vector. You can see A to B means like B minus 1, so 0 I, then minus 4, point minus 4 J, and 0.3 K. Okay? And now we have to just convert this one into Cartesian vector, but they are saying this is working vertically down, so you can see the force is basically minus 30 K. Okay? Now if I set the whole thing here, then my moment along the x-axis would be equal to I, so 1, 0, 0, then 0, minus 0.4, 0.3, and here is 0, 0, minus 30. So you can see basically this one, when you take 1, then basically this minus this. Okay, so this minus this is basically, let me write it down here, 1 into minus into minus, that's plus 12 minus 0, and then this one is 0 into something is 0, and the other one is also 0. So this one is actually 12 Newton meter. So this one can create 12 Newton meter. On the other hand, you can see this one requires 14 Newton meter to lose that one. So basically the answer is, since this is less than 14 Newton meter, so the answer is no, he will not be able to open that one with this force. Okay, maybe he has to apply a little bit more force, or he has to apply a little bit force which is a little bit higher than, like, or like at different direction. Okay, so if you see here, like, whether he can do that one, like open, if he change the direction here, then basically you can see if he makes this one perpendicular, then basically he will be able to $30 Newton. You can see that when he was using this one, that's actually for 2D cases. You can just think about like 2D cases. Like, let's say when the force was working down there, then basically the distance from here to the line of action, perpendicular distance from here, was 0.4. So if I multiply 30 into 0.4, that's actually my 12 Newton meter. Now, if I make that one, like perpendicular to this axis, this, like range, then basically the distance from here to here is 0.5. So the moment will be created if I change that direction along the x-axis. That would be 30 into 0.5. That's actually 15 Newton meter, which is actually higher than 14 Newton meter. So this means, like, if he changed this direction from here to here, then only he can be able to open that, like nut, lug nut, like with this 30 Newton force. The other way would be like just to apply more load, or he can just move from here to this direction, then he will be able to open that one. Okay, now let's move forward. Now I am going to show you problem number 4-60 here. You can see the figure is here, which is saying the A-frame is being hoisted into an upright position by the vertical force F equal to 80 pounds. So that's actually the upright, means like the working vertically up here, and this is your frame A. So determine the moment of this force about the y-axis when the frame is in the position shown. So they are asking to find out the moment this force will create actually in this axis. Okay, so don't be confused with the axis. This is the actual axis, but I'm trying to, even though they said like this is y-axis, but basically try to see that one as another axis, not like the y-axis here. Like any axis. My original axis is this. Okay, this. So I'm gonna find out the moment of this one along this axis here. Okay, So to do that, we know that the moment along any axis is basically the unit vector and then your position vector from, let's say, A to C, because this is A, this is C, and this is B. So let's say A to C, cross product of the force. Okay? Now I can just find out like what would be the unit vector to go from this way. Okay? But the thing is, like, to find out the unit vector, you need to first write the position vector. Then divide your position vector with the magnitude, so that for a unit vector the length would be only unit. Okay? So let's see, like, if I draw that one separately here, then basically let's say this is my y-axis, actually y prime axis, and this is my x prime axis, and this is the other axis. I have to find out the unit vector for that. Okay, so let's say this is the point A here, and the location of that point A is at the origin, so 0, 0, 0. Okay, now if I take any point which is unit length from here, let's say 1 feet here, then you can see the coordinate of that point is basically, this is 30 degree, so this is cosine 30, and this is sine 30. So the location of that point is basically cosine 30 and sine 30. But you can see actually in this figure, this is my x here, so the other side, this one, so basically this one x has to be negative sign here. Okay, now if I write a position vector from here to here, then basically you can see the position vector from A to C, that's basically minus cosine 30 I plus sine 30 J. Okay, that's the position vector. I already know the magnitude of RAC is basically 1. So my unit vector from A to C, that has to be same like the position vector, cosine 30I plus sine 30 sine 30J. Okay, now I have to find out the position vector AC. So I need to know the location of these 2 points here. So I know A is 0, 0, 0, and C is, you can see, in the other direction. So from here to here, this one would be 6 cosine 15. How about y direction. You can see this one is from here to here. Actually, this is a uniform A, so this one is actually at the midpoint from here to here, and you can see the distance from here to here is 6. So this distance from here to here is actually 3. And this is your z from here to here. So you can see if this is 6, then this one would be 6 sine 15. Okay? So my position vector A to C, that would be minus 6 cosine 15 I plus 3j plus 6 sine 15 k. Okay, and you can see our force vector is just going up, so this one is basically 80 k. So now I can put the whole thing here, like my my is basically, first of all, the unit vector here, so which is minus cosine 30 the sine 30. You can also put the value of cosine 30 and sine 30, that's up to you, in the matrix. I'm just writing this way, but that's up to you. And then this one is 0. And the RAC, so this one is minus 6 cosine 50. And this one is 6 sine 15. And for that force vector, you already know this is 0, 0, 80. Okay? So basically, if you find out the determinant here, actually you can just take this one first, okay? Because other 2 is 0 here. So I can say this is 80 into, so you cancel this one and this one, so this one minus this one. So this one is minus 3 cosine 30, and this one is negative and negative, that's positive 6 cosine 15 into sine 30. So that's basically 282 pound-feet. Okay? So that would be the end of this video. Thank you for watching.